Welcome back. Last time we cracked our first transistor circuit, the fixed bias circuit, wide open. The base current, the collector current, every voltage. But I closed with a warning. That simple circuit likes to drift, and here is why. In fixed bias, the base current depends only on R sub B, and the collector current is just beta times that. So I sub C rides entirely on beta, and beta is a slippery number. Swap in another transistor of the very same type, and beta might jump from 50 to 150. Your collector current triples. Your carefully chosen operating point slides towards saturation, and the amplifier clips. Today we fix that, and the fix is almost insulting in its simplicity. We drop one resistor into the emitter leg. That single resistor, R sub E, tames the drift. Let us see exactly how, by solving the circuit completely. Here is the circuit, and at a glance, it is the fixed bias circuit with one new piece. A 20-volt supply, V sub Cc, feeds the base through R sub B, 430 kilo-ohms, and the collector through R sub C, 2 kilo-ohms. Beta is 50, same as before. The new piece is down at the emitter. Instead of wiring it straight to ground, we send it to ground through R sub E, 1 kilo-ohm. That little resistor is the whole story of this lesson. As always, the two capacitors are open circuits in DC. They keep the AC signal out of our DC analysis, so we ignore them. The question asks for everything. The base current I sub B, the collector current I sub C, and the voltages V sub E, V sub B, V sub C, V sub CE, and V sub BC. Let us walk it exactly as we did before. Same tool as always, Kirchhoff's voltage law, and the same walk. We start at the supply, 20 volts. The current out through the 430K resistor has only one path, into the base, so it is I sub B. First obstacle, R sub B. We pay the toll, minus I sub B times 430K, and we arrive at the base. One step across the base emitter junction, minus 0.7, and we land on the emitter. Now, here is the new trap, and it is the single most common mistake in this circuit. We still have to walk down through R sub E to reach ground, so we pay another toll, minus the current through R sub E times 1K. But which current flows through R sub E? It is tempting to write I sub B. Resist that. The emitter resistor carries the emitter current, I sub E. Everything that came in the base plus everything that came in the collector pours out of the emitter. And we already know the relationship. I sub E equals beta plus 1 times I sub B. That is 51 times I sub B. So the toll across R sub E is minus 51 I sub B times 1K. Now we reach ground, 0. The full walk reads 20 minus I sub B times 430K minus 0.7 minus 51 I sub B times 1K equals 0. One unknown, I sub B, exactly what we wanted. Let us collect it. 20 minus 0.7 is 19.3. On the other side, I sub B times 430K plus I sub B times 51K, because 51 times 1K is 51K. Add them. I sub B times 481K. Pause on that 51K, because it is the secret of this circuit. The 1 kilo-ohm in the emitter, seen from the base, looks like 51 kilo-ohms. Beta plus 1 multiplies it. A small emitter resistor casts a giant shadow on the base loop, and that giant shadow is what will steady our current. So 19.3 equals I sub B times 481K. I sub B is 19.3 divided by 481K. Volts over ohms gives amps. 4.01 times 10 to the minus 5 amps, which is 40.1 microamps. Magnitude check. Base currents live in microamps, and 40 is right in the healthy 30 to 80 band. We are on track. I sub B is on the board, and the two currents that depend on it fall out in one line each. The emitter current we already used. I sub E equals 51 times I sub B, 51 times 40.1 microamps, which is 2046 microamps. Slide the decimal 3 places, 2.046 milliamps. The collector current, I sub C, equals beta times I sub B, 50 times 40.1 microamps, 2005 microamps, that is 2.006 milliamps. Magnitude check. Collector currents live in milliamps, and 2 milliamps is exactly right. And notice 2.006 and 2.046 are practically twins. There it is again, our old promise. I sub C is approximately I sub E. Now for something the fixed bias circuit never gave us, a voltage at the emitter. Before, the emitter sat at ground, 0 volts. Not anymore. The emitter current flows through R sub E, so the emitter floats up. V sub E equals I sub E times R sub E, 2.046 milliamps times 1K. Milliamps times kilo-ohms gives volts directly, 2.046 volts. And the base, use the junction we trust. V sub BE is V sub B minus V sub E, and it equals 0.7. So V sub B equals 0.7 plus V sub E, 0.7 plus 2.046, which is 2.746 volts. Now look back at this emitter voltage because it is the hero of the whole story. Suppose beta were larger and the collector current tried to climb. More current through R sub E means a higher V sub E. But V sub B is roughly pinned by the base loop. So a rising V sub E squeezes V sub BE, the base emitter drop, and a smaller V sub BE throttles the base current right back down. The emitter resistor is a leash. The harder the current pulls, the harder the leash pulls back. That self-correction is exactly why the emitter bias point barely drifts, while the fixed bias point wandered. One walk left on the collector side, and it hands us the last 3 voltages. Start at 20 volts, down through R sub C. The current there is I sub C, and we know it, 2.006 milliamps. The resistor eats I sub C times 2K. 2.006 times 2 is about 4.01 volts. So the collector sits at V sub C equals 20 minus 4.01, which is 15.99 volts. Now the first minus second rule, our rule for life. V sub CE is V sub C minus V sub E. 15.99 minus 2.05 is about 13.94 volts. That is V sub CE. And the last one, V sub BC is V sub B minus V sub C. 2.75 minus 15.99, which is minus 13.24 volts. Negative, and just like last time, that minus sign is good news. It means the base collector junction is reverse biased, and together with the forward biased base emitter junction, that is the signature of the active region. The transistor is amplifying, healthy. One sanity check before we close. The supply should split entirely across the 3 drops. The collector resistor takes 4.01. V sub CE takes 13.94. The emitter resistor takes 2.05. Add them. 20 volts exactly. Nothing leaked. Let us pocket the lesson. The method never changed. Start at a voltage you know and pay every obstacle around the loop. The only new twist was the emitter resistor. It carries the emitter current, not the base current. So in the base loop, it counts as beta plus 1 times its value. And that is the whole point of this circuit. In fixed bias, beta lived only on top, so the operating point rode entirely on it. Here, beta also sits underneath. in the denominator. When beta grows, the bottom grows with it, and the current barely moves. That is the negative feedback the emitter resistor buys you, and it is why the emitter bias point holds steady while the fixed bias point wandered. Our circuit came to rest at a comfortable, stable point, 40 microamps, 2 milliamps, and a collector-emitter voltage of about 14 volts. Next time we push the idea one step further with the voltage bias, the configuration real designs actually use. See you there.